No. Okay. All right. Let's start.
All right, so everybody ready to go? Before we start, does everybody load the toolbox from the USB drives? Because we're going to be mixing PowerPoints and MATLAB demos back and forth.
Are these the same ones that John did in GitHub?
Say what?
The GitHub?
It is a version, but the latest demo was on the USB, so very particularly the demo.
Yeah, so on GitHub, it was updated over like on Friday or Saturday. So if you downloaded cBathy prior to last weekend, I would use the version that was on the site.
Okay, so I redid it.
Yeah.
Or I'll be right out.
Okay, let's start. Ian Turner. Okay. And if you have any trouble seeing stuff, you probably should move to the front. Obvious. Okay, I'm Rob Holman. I've been doing Argus stuff for a long time, and I was one of the key developers on cBathy. So how many people have actually run cBathy? Okay, so for most of you, it's going to be the first time through. We're going to go through, I'll talk about some of the theory and reasons we do certain things, and then we're going to step back and forth into a demo.
Sorry, if you guys want to do cBathy, which is just the GUI version of this, you're welcome to join me. Follow me. Also, if you're in SurferCat, any last calls, I can show you where to go there too. Yes. Yeah.
Okay, we're back at it now that Brittany's interrupted. All right, we're recording this, so this should be available later online, and you can actually review it again. This is a great chance for you guys to ask any questions. So if there's stuff that's not clear, I encourage questions. So we'll start out with some of the background stuff. This is the plan for the day. So some background stuff, including the need for bathymetry and various ways you can measure bathymetry, shifting into remote sensing. We'll go by that pretty quickly. We'll settle into what's called dispersion-based bathymetry methods that look at wave propagation, and then particularly cBathy, which is a flavor that has a very different way of measuring wave number. It has three phases, 1 and 2, which are the real workhorses for doing the analysis. And then phase 3 is a Kalman filtering, which just is a good way to go through imperfect results and create a much better overall average result. So why do we need cBathy? Why do we need bathymetry? There's a lot of reasons. Actually, of all the measurements we make in the nearshore, bathymetry is probably the hardest and the most important because it's needed to predict others. But there's a lot of people who care. I've had a lot of funding from Office of Naval Research through my career, and that's because they have operational needs going across the shore. So Navy SEALs and Marines, since World War II and others, have needed to know the bathymetry, the situation that they're going to be facing operationally. On the civilian side, of course, there's a recreational side. The bathymetry has a lot to do with recreational safety, so development of rip currents, unsafe conditions. They want to know. For coastal zone management, bathymetry is probably the best measure of a beach's health. How much sand is there? How is it being redistributed? And finally, there's a concept of a nearshore prediction system. So the idea that a lot of the research we're doing and have been doing is to develop a predictive capability of how the nearshore works. And a key part of that is going to be having bathymetry. So let me walk into that one a bit more. We would like, as a community, to be able to supply products, and I've just given one example here on the right, which is a map of currents that were generated for the Duckfield site north of the pier. And this is work by Greg Wilson from OSU. And you'd like to take models, which is an embodiment of all our knowledge of physics, and be able to produce these maps for whatever societal reason there is. And I am not emphasizing on the details of that, but there are a number of models available. For this to work, you need good physics, but more to the point right now, you need good boundary conditions. One of those, the key one, is the bathymetry. That's the bottom boundary condition for the physics, and also the driving conditions, which is the wave forcing along the boundary. So the community has worked a lot to improve our understanding of the physics and test our understanding of the physics, including a bunch of field experiments here and in other places where you've measured everything as well as you possibly can. So you try to approach the situation of perfect data and find out how well the models themselves perform and then improve that physics. And that's good for testing models, but if the concept is to have nearshore predictive capability for any beach at any time, you're never going to be able to do the investment of money like you have in field experiments here. So you won't have perfect bathymetry conditions, you won't have perfect wave conditions. And the concept is, can we replace those with remote sensing conditions or instruments and algorithms? Those will be imperfect, they'll be an approximation. Because they're approximations, we'll have to use data assimilation in feeding the models. But that's like the goal. And there's good evidence that we are getting better and better at producing sufficiently good inputs to make good predictions. This is the essence of a concept called ICON, which is International Coastline Observing Network. And it's something we're trying to develop among different countries, where you would have observing stations regularly producing products, remote sensing products, that could be fed operationally into models and to just see how well you do. So one more comment about the need of sampling nearshore bathymetry in time. And this is just anecdotal. So this is another prediction that Greg Wilson did. And the prediction here is based on a survey done on 18 October 1997 during a field experiment. And the prediction is the blue arrows, and it shows a gyre here and a general southern longshore current. The measurements are in red, and you can see that the gyre direction is wrong. And so despite the fact that this prediction is for 20 October, and the survey was from 18 October, you can see you're getting the wrong direction. So there's reason to believe that the bathymetry and the boundary conditions that you're feeding the data with are at least as critical as maybe are some imperfections in the physics. So you need to measure bathymetry, and you probably need to do it traditionally or frequently. So everybody's familiar with some of the traditional methods. That's actually me. Serving on the Oregon coast. I think that's Peter Ruggiero. GPS has helped a lot. The crab, of course. People come to the FRF because it's one of the few places in the world that can measure bathymetry for you accurately. If you hadn't seen it, that's what the crab looks like without a cab. So that's from the 1980s. Traditional survey methods, they're accurate, but they're costly and they're infrequent. And especially if you're not at a site where they have this capability. So it's not an operational solution. Jet skis are a bit better. So the next question is, what can we do with remote sensing? And I'm just going to mention a couple of ways that remote sensing can be used to do bathymetry. One is multispectral techniques. And the idea is that when light penetrates into water, if it's clear enough water and bounces off the bottom, then you'll see that reflected light. But the amount of water it has gone through will determine the amount of attenuation. And the attenuation of the light is frequency dependent. So red light is attenuated faster than blue. And the result of that is that there are variations in the color as you see the bottom, with the bluer corresponding to deeper bathymetry. And so there's a lot of complications in this. It depends on water quality and the bottom reflection. And of course, you have to have clear enough water to be able to see the bottom. But people who have spent a lot of time on that. A very good solution if you have clear enough water is bathymetric LiDAR. So LiDAR is a really excellent instrument. Is sometimes mounted on planes, and they can fly over a region of interest. And if the water is clear enough, then the LiDAR beam penetrates to the bottom, and they can do time of flight measurements to get bathymetry underlying. It covers a large area. It does require relatively clear water. It's expensive. So it tends to be for situations like doing as surveys along the entire coast every 5 years or so. Then here's an optical remote sensing technique, which is based on dissipation estimates. This is something that Stefan Arnikoff in the Netherlands did as part of his PhD thesis. This is a time exposure image. And so the pattern of whiteness corresponds to the pattern where waves are preferentially dissipating, which is usually shallow water. And the idea is to be able to exploit that signal so that time exposure is a measure of incident wave dissipation. Wave dissipation is related to bathymetry in ways that can be expressed in models. And so the idea is, can you invert that relationship to take a dissipation pattern and find out the bathymetry that must have caused it? So this is, in the bottom panel, is a dissipation pattern produced by a numerical model, which was Dolph-TG, I think. And the idea is, and that pattern depends on an assumption of the underlying bathymetry. And so you run it, you compare the pattern produced by that bathymetry to the pattern you found in the time exposure, and then you twiddle the bathymetry until you get a better and better match. So that's what I just said. This was part of an algorithm called Beach Wizard from Deltares in the Netherlands. Obviously, it works best in the surf zone because you need braking signals. And it required a full numerical model to run for each gas. So it was a CPU intensive thing, but interesting. Okay, so that brings us, yeah.
How long did they run the model and a solution?
I don't know how many iterations. You know, it's a thing that the closer you are to the right solution, the faster you can converge. And so you get it running, you know, and you get an answer, and then the next hour you try to figure out how it's changed slightly.
I don't know if it was a probabilistic or deterministic inversion. So you know if it was a probabilistic or deterministic for inversion?
It was not a probabilistic.
Was it like just a square method probably to optimize bathymetry for dissipation?
Yeah, I mean, I don't remember the search algorithm, how it actually converged on a solution. But the basis of it was trying to match dissipation patterns.
The reason I'm asking is that there is this caveat of getting the local minima versus, you know, the global minima depending on the guess.
Yep.
So that could be an issue.
And, you know, honestly, it also doesn't work when there's no braking. So, but that's not our focus today. So our focus today, which is going to work very well when there's no braking, was using what we call dispersion based bathymetry relationships. So this is the linear dispersion relation given here, and it takes two characteristics of the waves and relates them with the function as a function of depth. So here's a picture of waves. One of the characteristics is the wave length, distance between crests, and it is described as either L or its inverse is 2 pi is the wave number, and a radial wave number is 2 pi over the wavelength. And then the other characteristics that we exploit is the frequency. So if you stood there and got hit by a crest, how long would you wait till the next crest hits you? So that would be the wave period, T, and the frequency is 2 pi over that. So those are the things that enter into the dispersion relationship. You can rewrite this to solve for depth. So divide by GK, take the inverse hyperbolic tangent of sigma squared over GK, and then divide by K, and you have a relationship for depth. And it's only a function of frequency and wave number and gravity. So if there were water on Mars, you could use this on Mars with a different G. So the idea of all of these dispersion relations based bathymetry things is to estimate frequency and wave numbers for a suite of frequencies and then solve for the H that best matches those frequency pairs, frequency wave number pairs. I put in here, ignore occurrence. The dispersion relationship does vary if you have a Doppler shift because of a current. We're going to ignore that for now. That could be some future thing. So we are not the first people to have thought of doing this. In fact, during World War II, they actually were trying to do exactly this problem because they needed to know. There's actually a paper called Determining the Gradients of Enemy-Held Beaches, which is from around that time, which is trying to use pictures of propagating waves, picking out crests to get a wavelength, and if you have a series of those pictures, then trying to get a frequency and estimate depth. So they cared a lot about bathymetry, and to the extent that if they didn't have a remote sensing method, they had to use Navy SEALs or somebody to go in, and it's an enemy-held beach, and figure out, well, at this location I'm at this depth, this location I'm at this depth. And so this was not a favorite task of Navy SEALs. So the good news about this thing was you didn't need Navy SEALs, and it could work in turbid water, so because you only need to see the waves. The bad news is it was awful. I mean, it was just that simple, picking out crests and periods gives you very noisy signals. Not very useful. The next step was to get a little more sophisticated in the analysis, and particularly the signal processing, and that was to use Fourier transforms. So if you have a bunch of data in spatial maps, X, Y, and in T, then you can do a 3D FFT. So that will invert in frequency to give you, in time to give you frequency, and in the two space domains to give you the components of wave numbers. This is what the dispersion looks like for a particular depth. So it's this parabolic conical thing. And the tightness of the cone depends on depth. So if you measure waves out in the real ocean, they should lie on this surface. And so the idea is to do a bunch of these maps, XY, maps of waves in time, and do a 3D FFT. It's hard to visualize a 3D FFT in two planes, but you can look at like the intersection to a X equals some value, and you'll see the parabolic shape. This is work, by the way. Oh, no, I'll get to that. And this is one of those transects. So they have taken data, and this is a slice through the 3D FFT. And you can see that the roughly parabolic shape with a bunch of clutter around it. And this is what you would like to exploit. This is the basis of some Fourier methods. One is called the Fourier stacker, principally by John Dugan, who's from Arete, it's a consulting company. And this was done in the around 2000s. And then there's a version called XMFit, which was done by Josh Friedman at Deltares. And these exploit these 3D FFT curves. There's a couple of problems. First is useful ocean waves that actually feel the bottom and that you could exploit are a small part of this domain. Once you get too high frequencies, they don't feel the bottom, and too low frequencies, they don't exist. So that's a problem. But the bigger problem is doing an FFT in space. When you do an FFT, you're mapping between spatial variations and wave numbers, cycles that fit into this box, this analysis box. And a usual FFT does a set of wave numbers. One cycle fits within the box, two cycles fit within the box, three fit within the box. But you're actually using boxes that might look like this size. And that's only two wavelengths. So this is not what Fourier transforms are designed for. The other thing that's odd is you only get one estimate per box. And so you can shift the box a little bit each time, and in that way sort of figure out the convolution of the box over bathymetry. But it's really not a method that's well designed for high resolution bathymetry, especially in shallow water where things are changing a lot. So that gets us to cBathy, because we're going to do a completely different way for solving for wave number. So I'm going to say a couple of general things about the motivation that got us into doing this. We wanted to develop an algorithm for bathymetry that could be driven completely by remote sensing. And EO means electro-optical, which is Navy and other military speak for optical. You get better funding if you say EO. Or it could work with radar. And so it's just you've got some remote sensing data that you feed in, and cBathy will tell you what the resulting bathymetry is. That you'd like it to have sufficient spatial resolution that the important things in the near shore are resolved, like sandbars. And so it has to have small footprints of analysis, not big footprints of analysis. You'd really like it to be robust, because you know about me and Argus, we turn on Argus stations and then they just run. And if anything required manual intervention, we wouldn't be doing it. So being robust means it has to be immune to things like fog, rain, etc. That doesn't mean it provides an answer when it can't see. It means it gives you a confidence intervals that tells you, I have no idea what I just saw. And so it's important that you get estimates and confidence intervals that work. Also, and I mentioned about that dissipation-based beach wizard, that required running an expensive numerical model a lot. It'd be nice if you didn't have to have a numerical model, although if you wanted to get fancier later, you could. So what we'll talk about is cBathy. This was first published in 2013, what is now called version 1.0. There's been a few upgrades during different Argus workshops. We are now on version 2.0. This was published in 2021, and it is a lot better than the version 1.0. So don't even think about using the early version. They are both, I believe, supplied on CIRN GitHub. So if you want historical stuff. Why is it called cBathy? So this is the dispersion relationship that we're using. When waves progress, the speed of progression goes one wavelength in one period. And so the speed which is given the symbol C, is the frequency divided by the wave number. That's equivalent to the wavelength in one period. It's called C instead of just U or some velocity because it's the movement of the form. It's not the movement of the water particles. And so celerity, I think, is, I don't know, a Greek term or something that talks about movement of form. But the symbol is always C. And so C, we can re-express the dispersion relationship in terms of C and find a bathymetry. And it's even simpler in shallow water. If you look at hydrodynamically shallow water, when waves get shallow enough, the speed depends only on bathymetry. And so the idea of cBathy is that you can invert that relationship to get bathymetry. And so cBathy was a cute little name. If you've got C and potentially K, if you're in intermediate water, then you can estimate depth. In fact, we never estimate celerity. So it's called cBathy. We never estimate celerity. You can if you want as a byproduct. Okay, so the estimation. This is the relationship we're exploiting, frequencies and wave numbers. So we need to estimate frequency and wave numbers. And our basic input data that we get to work with for us is image intensity, I, and our maps, function of X, which is cross-shore for me, Y, which is longshore, and then their time series. So we get a bunch of these maps, basically, every half second for 17 minutes. And we want to exploit that. So the first thing that is interesting to think about with the cBathy data collections, and it's the same with all the pixel tools, there's one of the facts of life of video is that video data is like drinking from a fire hose. That, you know, the cameras are 5, 12 megapixel. They run at 30 hertz. This data set here uses 6 of them. And so it's just a giant volume of data, most of which we don't know. So I can estimate bathymetry by looking at a small subset of those in a grid, a cBathy array, with a typical sample, and we're going to end up using like 5 meters in cross-shore, 10 meters in longshore. That's plenty to describe waves. So this is part of the pixel toolbox. We take the original time series, we cut them down to 2 hertz, and we cut them down to a regular sampling grid, which is often 5 by 10 meters, and just save the time series, 2 hertz time series from those pixels alone. And I'll talk more about sampling in time and space in a minute, but that's roughly a factor of 10 to the 4 in sampling compared to if you took the data streams from all the cameras. You only need 1/10,000th of that to do really good cBathy. So the pixels we're using are all the blue here, and this is actually only half of them because if I plotted them all, you wouldn't see the ocean behind it. So it looks like, compared to fixed instruments, it's like this huge dense array, but compared to video, it's just a teeny fraction of what's available. But it's plenty to do what we want to do. So we do that. This is 13,000 pixel locations spaced in X and Y. Okay, that's the input data we get to work with. Now, how do we do this? We need to estimate frequency and wave number. We have the input data. Now, the frequency is easy to do, and it works well with Fourier transforms. We typically sample for 1,024 seconds, so that's 17 minutes or so. And that's a standard Fourier number. It's actually 2 to the 12 seconds, 2 to the 11 seconds. It's one of those powers. And if you know anything about Fourier transforms, when it was originally designed, it was important to have powers of 2 to do the analysis. And we still do. So if you've got 1,024 seconds, and you're trying to sample 8-second waves, that's typical ocean wave, then you're getting like 128 cycles. in your sample. And so that's great for Fourier transforms. They can resolve that really well. So we don't have to worry about the time. We do have to worry about the space. As I said, we would like to be sampling of order of wavelengths because things like sandbars that we want to resolve are ocean wavelength sort of scales or so. So we can't do Fourier transform in space. And what we do instead is we use a trick to get wave number out of what's called Fourier phase. So how many people are Fourier transform people? Some.
What do you
Not.
mean by Fourier transform?
How many people are comfortable with Fourier transforms? About half. Okay. I'm going to go through just some of the basics of Fourier transforms just to show what I mean. So the idea of a Fourier transform is that the ocean wave you see, which can be pretty complicated, it can actually be decomposed into the superposition of a bunch of individual pure sine waves. So I've done it in the forward method here, where I've taken 5 different waves and I just made up periods and I made different phases for them. So there are all these time series and I add them together, and that's the superposition. So this looks like a fairly complicated just stochastic wave field, but it's actually only decomposed or composed of 5 individual frequencies. So the assumption is there's this, for some time series that we measure here, there is a set of waves that went into making that. Now Fourier transforms let us objectively pick out which waves went in to make it. Because this, in that case, I told it which waves. So the nominal equation is that a sea surface elevation signal, so this is something, I'm just doing this as pretend you had a pressure sensor and you're just measuring in time, some time series. And so eta would be a sea surface elevation, and it looks complicated, but I can decompose it into a bunch of cosine waves and sine waves. The reason I do cosines and sines is that allows there to be different frequencies, different phases. So it could have started at this time, or it could have started 90 degrees later in phase. And so if you do both of those, you get, you can do phase. There are frequencies. So if tau is the length of the record, 1,024 seconds, then you get a frequency from j equals 1 to n at 1 over 1,024, 2 over 1,024, 3 over, etc. So you get a series of frequencies that add together. And you can express it either this way with the sines and the cosines, or equivalently, you can express it as a magnitude, capital A, the time variation with the frequency. So the sigma is I over tau, and then the phase, some phase. So you can either do the cos and the sine, or you can explicitly say what was the phase. The frequencies are just j over tau, or tau is the record length. N is the number of frequencies. So when you do a Fourier transform, say if I had n, samples, which for us we'd do 2 hertz, so it'd be 2,048 samples. You're estimating 2 coefficients A and B for each frequency, and so you get 1,024 frequencies. All right, so that's the number of degrees of freedom you have. A's and B's are the Fourier coefficients. So there's nothing more to calculating how much of this frequency and that frequency went into it than you just do a Fourier transform. And you get all the A's and B's back as the Fourier coefficients. They're usually expressed as a complex number, A plus IB. Right. But you get that in MATLAB, you just say FFT of the time series, and you get all of the A's and B's for all of the frequencies. If you want to express it instead of A's and B's, if you want to express it in a magnitude and a phase, the magnitude is just A squared plus B squared, all square root. And the phase is just the arctan of the B divided by the A. Okay. So that's the phase. And this is an example that I got on the web somewhere, that you can take some signal, a square wave, and you can actually decompose it approximately as the beginning, as a wave that fits in with 1 wavelength, 3 wavelengths, 5, 7, and then this is the sum of all these. So that's with 1. Now you've added another one, it gets a little bit flatter. But this is a mathematical truth that you can decompose any signal into its Fourier coefficients just by saying FFT. It's great.